Good evening, everyone. Today, let's embark on a journey billions of years into the past to explore one of science's most fascinating mysteries: the origin of life. Abiogenesis, or life arising from non-living matter, isn't just a scientific concept. It's a tale of chemistry and chance that paved the way for every living organism we know today, including us. From the fiery beginnings of Earth to the first microscopic spark of life, let's dive right in. To understand abiogenesis, we must set the stage. Over 4.5 billion years ago, Earth was a young, violent planet. Volcanic eruptions, meteoric bombardments, and an atmosphere filled with gases like methane, ammonia, hydrogen, and water vapor defined this hellish world. Oxygen, the gas we breathe today, was notably absent. Yet these harsh conditions were perfect for chemical reactions vital to the emergence of life. It was a cauldron of possibilities. Scientists theorize that Earth's early environment acted like a giant laboratory. Energy sources such as lightning, volcanic heat, and ultraviolet radiation triggered chemical reactions among simple molecules in the atmosphere and oceans. These reactions birthed basic organic compounds like amino acids and nucleotides, building blocks of proteins and genetic material. Laboratory experiments like the famous Miller-Urey experiment in the 1950s showed that such compounds could indeed form under simulated ancient conditions. It was the soup of life bubbling with potential. But life isn't just about simple molecules, it's about organization and complexity. Over time, these molecules interacted, forming more complex structures like polymers. Amino acids joined to form proteins, and nucleotides combined into RNA. RNA, in particular, is considered a crucial molecule in abiogenesis due to its dual ability to store genetic information and catalyze chemical reactions. Imagine these molecules as the first architects of life, laying the foundation for the biological world. Now, let's talk about protocells. Tiny cell-like structures that served as stepping stones to life. In the primordial world, certain lipids naturally assembled into vesicles, creating membranes. These membranes enclosed the organic molecules, protecting them and enabling more complex interactions. These protocells marked a significant step toward living cells, as they provided an environment where chemistry could evolve into biology. Abiogenesis is an ongoing field of study, and several hypotheses attempt to explain its details. For example, the RNA world hypothesis. This proposes that self-replicating RNA molecules were the first living systems. Hydrothermal vents, underwater volcanic vents, rich in minerals and heat, could have provided the perfect environment for life to begin. Panspermia. Some scientists suggest that life's building blocks, or even life itself, might have originated elsewhere in the universe and arrived on Earth via comets. Each hypothesis adds a piece to the puzzle, but none tell the full story. Yet, after millions of years of chemical evolution, the first true cells emerged. These cells were likely simple single-celled organisms resembling modern-day bacteria. They could harness energy, replicate, and adapt to their environment. This marked the transition from chemistry to biology, a moment so profound it changed the course of Earth's history forever. The study of abiogenesis doesn't just answer questions about the past, it inspires us to think about the future. If life could arise from non-life on a young Earth, could it also happen elsewhere in the universe? Abiogenesis reminds us that life, in all its complexity, started from the simplest of beginnings, a powerful testament to the wonders of nature and the relentless march of evolution. Thank you.